All right, so we have two last sections, reaction mechanisms, we're going to do today. The Arrhenius equation we'll look at on Monday. Okay, so reaction mechanisms we did in Chem 1, pre-AP Chem 1, where we had to add them up and we decided what were, I think we decided what their intermediates were and what the catalyst was. Can't remember how. Yeah, it was at the very end of the year, so usually y'all are burnt out by then. I don't know what you remember. But, yeah, it's like the little, we did like a little, like small part of kinetics. Small part of kinetics. Okay, so reaction mechanisms are, remember, whenever we see an overall balanced equation, it does not tell the whole story. Whenever we see that, we're seeing what they start with, what they end with, okay? It's, yeah, see that there, Twan says it's ringing a bell over there. So, but basically there's actually multiple steps it can go through, and usually there's a slow or a rate determining step, and then that determines how quickly the reaction takes place. So before we do that, we need to talk about some of the vocab that we need to take care of, and that is the elementary steps and molecularity. A mechanism represents the sequence. What we see as a balanced equation, again, is the overall part, okay? Must be determined by experiment, and it has to agree with the overall stoichiometry, and it must agree also with the rate law, okay? There are a couple of kinds. One of them is unimolecular, which involves one reactant molecule that collides either with the solvent or the background molecule. Bimolecular means you've got two reactant molecules colliding, and termolecular means you have three or more, and they're very, very rare. Very, very rare to have termolecular. Okay? Rate expressions for elementary steps are, the rate expression can't be predicted from the overall stoichiometry, but the rate expression of an elementary step can be. Okay, just of that step. Okay? Here is the rate expression to go with those terms that we just discussed. Okay, so of course, just from the kinetic, I just made up a word, that's kinetic and collision put together. Kinetic molecular theory, remember all particles are in motion, and of course, the more molecules you have colliding, and then collision theory says higher rate of collisions means more effective collisions, so you would have a faster rate. And of course, the faster the molecules are moving, the more likely they are to have enough energy, kinetic energy, to overcome their activation energy. When we're talking about molecularity and order, an elementary step in the reaction can be written just for its molecularity, not true of the overall reaction. Okay, so let's look at this example. So here would be a possible mechanism for this particular reaction, and one of the things we want to do is we want to double check that this adds up to the overall equation that we're looking for up here. So remember how we add everything up like a math problem? If it appears on the same side, we add them together. If they're on opposite side, what do? Cancel. Okay. So if I look at these first two, I see that these are going to cancel. So I cross those out. Right? Anything else cancel? N2O cancels. And that should be it, right? So then I add the three of them up, and I should get 2NO plus how many hydrogen? 2H2. It's going to yield an N2 plus 2H2O. Okay? The things that I crossed out, do you know what they're called?
They don't participate in the reaction.
They do participate in the reaction. They're intermediates.
Yeah.
Okay? So the way you recognize an intermediate is it's created and then it's used up in a subsequent step. When we get to catalyst, you'll see that's not the case. So an intermediate is created and then used up. So it doesn't appear in the overall equation, okay?
Because they're not there in the.
Because it got used up. But without that intermediate, that reaction would not proceed. It's just part of it doesn't show up at the end. So that's kind of showing you how that reaction mechanism works, and that I got to create that N2O2 in order for it to happen, because that's what actually reacts with the hydrogen. Okay? Created and then used up in a subsequent step is an intermediate. That's how you can recognize it. In a second, when we look at catalyst, you'll see that catalyst will start out as a reactant and then ends up as a product. So you end up canceling them out because they're appearing on both sides, but you start with it and you end with it because it's not used up. Okay, so when we're talking about, those steps would have been, all three of those steps were bimolecular because you had two particles colliding. Okay, forgot to answer that part. So the reaction mechanism and rate expressions are determined by experiment and must agree with the experimentally determined rate law. The slowest step is your rate determining step, meaning how quickly it will proceed. The rate of the overall reaction is limited by that slowest step. So basically you just start writing the rate and then add them up till you get to the slow step and then you stop. Okay, so we're going to do I'll show you an example. It makes more sense to do an example. Your reaction intermediates are what we just talked about. You create them in one and then use them up in a subsequent step. That's how you know it's an intermediate. And then, of course, a catalyst. What's a catalyst? What is it?
Speeds up a reaction without being burned up.
Very good. Very good. Now you're on the video.
Oh, really?
Yeah. So catalyst will, and how does it speed up the reaction? What does it do? It lowers the activation energy or provides an alternate pathway. But when you were putting a catalyst in there, you're lowering the activation energy, so it speeds up the reaction. But what is the same regardless of whether you have a catalyst present or not? The change in energy. So your products and reactants are still going to be at that same energy level. You just get there faster. Okay. Kind of like speeding to Dallas. Either way, you're going to start into the same place. But if you're speeding, you get there quicker. You might get a ticket, but don't speed. It's not safe. It's dangerous. Just giving you an example. Okay. Don't speed. It's against the law. And it's dangerous. Okay. So here in this example, we have this balanced equation. And we have the suggested mechanism. And so we want to know, is this an acceptable mechanism? And if it is, does it satisfy? So we got to justify. So when we say justify, that means we use words, not math. Okay? So if I add them up together, first of all, let's double check that it adds up to make what we need. So I would have what crosses out? All of it. Yes, that's right, Ajay. All of it.
F crosses out.
F crosses out. And that should be it.
Yeah, that's it.
So we add it up, we get 2 NO2 plus F2 yields 2 NO2F. Okay? So the suggested mechanism, we stop at the slow step. Okay? Intermediates never appear in the rate law. Okay? And so I would write this as rate is equal to K, and then NO2 to the first order and F2 to the first order. Okay? And then, of course, it gave us our experimental there. And so it is the correct mechanism. And the reason the justification is, first of all, it agrees with the stoichiometry. And second of all, it agrees with the experimental rate law. Okay? By stopping at the slow step. Never go past the slow step. Okay? The slow step is not always your first step. Sometimes it's the second, sometimes it's the last. Okay? Any questions on this? And those would be, they gave you a fancier explanation, but
I don't get how you know if it's fast or slow.
in this case, they told us. But that's not always the case. There are times when you will have to figure out what the slow step is.
How do you do that?
Usually if you know the rate law, you can figure it out based on that. Yeah. Yes?
So what's the whole thing with, you said like stop and slow step?
As you stop writing the rate law at the slow step.
So
So that's how we know that this wouldn't be NO2 to the second order, even though NO2 appears right here, because the slow step is the rate determining. After that, it doesn't affect the rate. Doesn't mean it's not important, because you still got to have that next step for the reaction mechanism to happen. But usually it's so fast that it's like instantaneous. So what's going to determine your rate and what affects it is the rate determining step.
okay.
Okay. Okay, so let's move on.
So this one's slow because the top one you had to break a bond, is that why?
No, because sometimes it's the second step that's slow. It's slow because they told us it was the slow step. It's been determined. They're wanting us to see if it agrees. And we're going to practice some on your worksheet in a second. So catalyst, we just talked about that. When we're drawing, if you ever have to draw, and that's actually a common occurrence on the AP exam, is they'll give you a graph, an energy graph, and say draw it catalyzed. Okay? Your main two things you need to make sure of is you start and end at the same energy level that they started and ended in, and then you just draw your hump lower, and because it's got a lower activation energy.
But they both, the overall difference is still the same.
The overall energy difference is still the same. Okay? So notice on both of those, I started and ended in the same place, but when it was catalyzed, I had a lower hump because my activation energy is lower. So that's how you would draw that. Okay? You already know, especially if you are in AP Bio, if you have biological catalysts, we call those enzymes. And then different kinds of catalysts. Homogeneous means same. So they would be in the same phase. So that means if you were working with liquids and you had a homogeneous catalyst, you would have a liquid catalyst. And then heterogeneous catalyst, of course, means they're in different phases. And then you can also have acid-base catalyst. And this is a cool reaction. If you've never watched that, it's all you mix together is sucrose, which is table sugar, and sulfuric acid, and we call it the carbon monster because this little black thing literally just grows straight up. Okay, the reason that we don't do it as a demo, I used to way back in the day, but it produces an enormous amount of heat and it smells bad, like really bad. No. And it pretty much ruins your glassware that you do it in. Yeah, it smells really bad. Yeah, but it's cool because it literally just grows. Some people call it the carbon snake, some it's the carbon monster.
Oh, yeah.
There's a demo.
Wait, isn't that a reaction people do like at 4th of July or something?
I don't think they do this one at the 4th of July.
No,
You wouldn't want to touch it. After it cools, you can because it's just carbon, but during it, it produces an enormous amount of heat. And it stinks like bad, like set off the fire alarm kind of
Wait,
thing.
what's that one where you like start it and then the thing curls out of a tube and it curls?
Oh, that's probably elephant toothpaste?
Oh.
Yeah. So here are the mechanisms for catalysts. I'm going to let you read through that because you are all proficient readers. Okay.
No,